Okay, so I'm Ariel Siegel, and I've been doing trusted computing research for a rather disturbingly long time now. In terms of my plan for this class, first off, this is the first time this class is being taught. This is the first time these slides are actually being used in practice, and I'm going to apologize in advance because I'm sure that I'm going to have screwed up the timing somewhere. I've tried to build in flex time in both directions just in case, but we may not stick exactly to the schedule as planned, just so you know. This is a little bit of a fire hose of information. So speak up if you get a little confused. Yes, you know, real shocking, this is totally my style. If you get confused early, you will probably stay confused. So if you're a little lost, if you hit a term that you don't know, or a concept you don't know, or you don't understand why I'm saying something, stop me and ask the question. We are going to start at a high level, and because I kind of gave you the 1,000-foot view. And then we're going to start zooming in this afternoon with both a little bit on applications. And I'll be perfectly honest, we are not going to get too detailed into any applications, partly because this is going out on the network, although the big enterprise applications talk is the one that may get cut because I'm borrowing somebody else's slides. And also just because there's a lot of people here who have enough different use cases that I didn't want to drill down into any one use case in too much detail, especially because, frankly, implementing any of those will take weeks, so telling you about it in enough detail to implement it would probably take a class in and of itself. We do have, actually, we'll just start with today. Everybody here seems to be pretty coming from a security background. So would anyone like me to go over the 30 seconds, basically it's not quite 30 seconds, but about 2 minutes of quick vocabulary review to make sure that we're all on the same page with things like nonsense and hashes? Well, Jim's watching the course and would like me to do that. So okay, we'll do that. So we'll do a very brief bit of background just to make sure that everyone knows the core, tools that we'll be using from security. Then we're going to go into a high-level discussion of what we mean when we say trusted computing. Then we get to start going into the real meat of the course. The TPM 101 talk is the one that I sort of half expect to end up running through lunch if I'm not careful, because it's all about what the TPM does. We'll talk a little bit about trusted computing beyond the TPM, and the other technologies that we'll be using, and some of the high-level stuff that's coming out of the Trusted Computing group. This afternoon, we'll do what we envision right now for large-scale enterprise TPM deployments. This tends to not be the very detailed applications like Zeno's talking about, where we're using it for timing on one machine. This is much more about high-level stuff. For TPM provisioning, we're just going to start getting into the deep dive. This is where you probably don't know all of the information involved here, even if you've been working with TPMs for a while. These talks are going to start getting into what the TPM, how you actually use it, what you actually need to do to make use of it. We're not going to get to programming it till tomorrow, and even then we're not going to go into any detail, but this is going to tell you a lot more. So you don't just say, oh, it's a TPM key, but what kind of key is it? What's it good for? What can I do with it? And tomorrow, we're going to be continuing the deep dive with, I'm focusing on functionality here. So we're going to talk about authentication and attestation with the TPM, which is really where my heart lives. But also data protection and storage, because I know a lot of people are very interested in TPM for those purposes, and some other things like those timing techniques that Zeno's talking about. We will talk about programming for the TPM, although I will warn you in advance that talk has a lot more to do with why programming for the TPM is a pain than how to actually do it, although we will talk about it a little bit. And tomorrow afternoon, I'm currently planning, partly the flex time for the slides, and partly, if people are interested, having a chance to talk about your use cases. And this is the other part that Zeno will cut out for the public discussion. a chance for you guys to say, well, here is what I want to use TPMs for. Let's talk about, can it be done, how can it be done, to whatever level you feel comfortable doing with the group. And if it turns out that nobody wants to talk about that, we can have a special bonus presentation on virtualization and TPMs, which is most of what I do. So, with that, any questions before we start getting into crypto basics? Awesome. So, this micro talk is not, this is sort of computer security in 5 minutes or less. So, again, if you get lost, speak up quickly. This is not, by the way, printed out in your booklets because I threw it together last night. So, first, when I talk about security, there's generally 3 principles that I'm talking about here. Secrecy, where there is some information that I want somebody else to not have because I want to keep it secret. This is the one that most people, when they think about security, mean, is there's a secret, it doesn't get out. Integrity means that I have some data that is still in the same state that it originally was. Signatures have something to do with this, so that I can say, I say that X is true, and I know that when it gets to you, it still says X is true, and nobody has changed it so that I said X is false. This also has to do with protecting the integrity of data on your own system, that if I think that my system is in state X, and it is now in state Y, I have lost integrity, something has changed, I want to have control over when things change. And then there's availability, which is in fact part of security because a brick is very secure, but it's not very useful. Trusted computing focuses on the first 2, sometimes at the expense of the third. We try very hard to avoid that, but let's be honest here, this is where the trades of trusted computing really come in. The more you are willing to risk the third, the more powerful you can get the first 2 in the trusted computing world. Because there are balances there, because if you keep it secret from everybody, including yourself, you've just lost availability. So, we'll be talking more about that, but just some vocabulary. Okay, another concept that we'll be covering a lot when we get to attestation is the concept of data freshness and of something called a nonce. Now the idea here is that we want to be able to say, this particular message, this particular report, this particular file, is this the one you sent me now? Or is this possibly one you sent yesterday, or 3 weeks ago, or this morning before you did a reboot? We want to be able to tell, is this message part of this transaction we're having right now, or not? Well, we can't really reliably tell not, but we can tell, is it current? And the tool we use to do that is called a nonce. The idea here is this is a freshly generated random number, which is to say we're basically drawing a bunch of random bits from a hopefully random piece of hardware and saying, the chances that somebody else managed to predict the same number that I was picking is so low as to be effectively non-existent. Therefore, if I see that number in use again, I know that whenever that number was used, it at least happened after I generated the number. I don't know by how much. So usually these are used for a single communications session. But I've at least put a boundary on when that information was created and utilized. So the key pieces of nonces are, for one thing, they're not any kind of universal idea of, is this recent? If I generated the nonce, I know that at any time I see that nonce, it came from after I generated it. If I generated this nonce, Glenn does not know anything about how recent something is because he doesn't know that I generated it freshly. He doesn't know when I generated it. So in general, when we do have protocols that use nonces, everybody who wants to check that something is fresh is going to be using their own. One of the questions we get a lot is, well, can't I just use a timestamp? And can't the TPM provide me with a timestamp? The answer is no. Calibrating timestamps is problematic in and of itself. How do I know that your sense of time is mine? But more critically, timestamps are predictable. So if I have a report that says it was generated on May 30th, 2011, I have no reason to believe it was actually generated on May 30th, 2011, because you knew last week that May 30th, 2011 would exist. So you could generate that in advance, and I would have no way of knowing that this actually was generated then versus just having time. So this is why we use nonces and why random numbers are a thing that we actually want quite a lot in this world. So cryptographic keys. There's really two main categories of cryptographic key. Symmetric keys and asymmetric keys. And asymmetric keys are also what you will often hear called private keys or public-private keys or public key cryptography. All of those refer to asymmetric keys. So symmetric keys are, there's lots and lots of algorithms. We're not going to go into any detail of symmetric key cryptography today. Go look at a crypto class if you really care. But the idea here is that you have the same key that is used for all operations. I encrypt data and I decrypt data with the same key. I sign data and verify data with the same key. You don't usually use symmetric keys for signing, but if you were going to, it's the same key for all operations. Symmetric key crypto is great stuff for speedy operations, for bulk encryption, tremendously useful. The problem, of course, is that it's the same key for everything. Those keys need to be secret at all times if you're going to use them as a key and not merely decorative. That means that key distribution is a royal pain in the neck, and it doesn't suit most large-scale operations, because how do I make sure that you have the secret key to share with me if you don't have it already? So we aren't going to be talking about symmetric keys very much in this class, but I will be mentioning them and passing a few times because we often use them to augment what we're doing with TPMs because of this speed factor. And this is a question that people will ask a lot, and we'll get to it again later, but the TPM does not do any symmetric key cryptography because of export control laws. So it does use some internally, but you can't get it out. So the other big type of cryptography is asymmetric cryptography or public key cryptography. And in this world, keys are paired. You have one public key and one private key that are associated with each other. A public key is public. You can publish in the New York Times and nobody's going to have a problem with that. The private key must be kept secret. And this is a tremendously powerful tool because it means that we use the private key to decrypt data and to sign data. But anyone can use the public key to encrypt data to me or to verify that a signature came from me. So this means that we have a concept of identity because I have the private key, but everybody else can check and make sure using that public key that I'm me and that certain data is associated with me. Now, the reason you don't actually see these used for everything is because most public key crypto algorithms are quite slow. These are not something you really want to use for bulk operations. Some of them can't even be used for bulk operations. Some of them have ceilings for how much data you can put in. We are, in general, today, if I say this is a public key pair, or there's a public key or a private key, I mean an RSA key. This is not the only kind of public key that's out there. It's not the only public key algorithm that's out there. There are some great ones coming down the pipeline. And one of the big questions we get is things like elliptic curve cryptography. Yes, it exists. TPMs today do not support it. TPMs today use RSA for pretty much everything. So when you hear me say public key or private key, right now you can just assume I'm talking about an RSA key. And in the future, in the next generation of TPMs, we will be seeing better algorithms come out. But today, I mean RSA. If the phrase RSA doesn't mean anything to you, don't worry about it. It's a magic phrase for an algorithm. So, hashes. A cryptographic hash is a one-way function where I can take arbitrary data and I will turn it into basically a fingerprint, something that uniquely identifies this data. And there are a few properties that make something a cryptographic hash. One of them is it should be really easy and fast to calculate because we use these all over the place. The second of which is if I've got a hash, I should not be able to look at that hash and immediately say, oh, this came from this data. It should be easy to go from data to hash and nigh impossible to go from hash to data without having the data on hand already. It should be extremely difficult to find collisions where, realistically, I'm taking arbitrary length data and I'm turning it into what in this case is a 20-byte hash. That's fixed length. We've got arbitrary data in the world. There clearly collisions exist because we're taking arbitrary infinite numbers of possibilities and turning them into finite possibilities. There are collisions. We want them to be as hard to find as possible so that I cannot make it look, for example, like I've signed data X when I've actually signed data Y. We also want to make it very difficult to be able, if I modify anything in my data, we want it to be visible in the hash. Because the main thing we use hashes for is auditing and checks on, basically we use it for as a primitive form of measurement. Is this the data we thought it was? So we want changes to show up. In general, when I talk about hashes in this class, I'm talking about SHA-1 hashes. These are the ones that go to 20 bytes. Again, there are more recent algorithms out there. They are not yet widely supported in hardware. For those of you who've heard, well, SHA-1 there are attacks on SHA-1. There are attacks on SHA-1. They have not broken SHA-1. They have made it a little bit easier to find collisions, but it is not in the realm that we are really concerned about. So for now, we are treating it as good enough for today, good enough for tomorrow. We're working on getting the new ones out the door. But today, if I talk about a hash, I mean a SHA-1 hash. And again, that's the name of an algorithm. If it doesn't mean anything to you, don't worry about it. Also, a couple of common attack terms that will come up again and again. First, denial of service or DOS. This is an attack where somebody causes your service to not exist. This just is about lack of availability, and you can do this to yourself. We call it a DOS attack, but frankly, I can DOS myself, and usually in the trusted computing world, when I'm talking about DOS, that is generally what I mean, because it's very easy to shoot yourself in the foot if you're not careful. A man-in-the-middle attack is much more interesting. This is an entire family of attacks where I have some adversary who's sitting between two parties, or more than two parties if you are doing complicated protocols, and forwarding messages between them, potentially modifying them if the messages are not signed, in such a way that the two parties think that they have completed a protocol successfully, but some of their assumptions are wrong. So for example, if I think I've run my protocol successfully with Lisa, and Lisa thinks she's run her protocol successfully with Glenn, this is a problem. Or if I think that Lisa has signed data X, and Lisa thinks she signs data Y, that's a problem. And man-in-the-middle attacks tend to come from protocols that have been badly designed so that messages can be forwarded around or replayed. Sometimes you'll see these where, Lisa completed a protocol quite legitimately this morning, and then I'm seeing her responses this afternoon, but I think they're current. So there's a lot of different variations on man-in-the-middle attacks. Mostly just know what the word means, so when I tell you that they exist, you have some idea what I'm saying. So that's the lightning security review. Are there any questions?